Some math skills that you're expected to have when you sign up for an algebra-based physics course, such as the general physics course that we teach at St. Anselm College, but we expect you might be a little rusty on it. We'll start off talking about powers and begin with some manipulations involving powers of 10. Suppose you're asked to evaluate the fraction 10 to the 9th times 10 to the 4th times 10 to the minus 7th divided by the product 10 to the minus 3 times 10 to the 7th. In multiplying powers of 10, you just add the exponents. So here we get 9 plus 4 is 13, plus a minus 7 will give us 6. So we got 10 to the 6th divided by, here, this is the product of 2 powers of 10 again. We just add the powers, add the exponents, we get minus 3 plus 7 is 4. 10 to the 6th divided by 10 to the 4th. In dividing powers of 10, you subtract exponents. So we'll take, we get a result of 10 to the 6 minus 4, where our answer is 10 to the 2. Okay, next. How do you deal with fractional powers? What does an expression, for instance, like 7 to the 1/4 mean? 7 to the 1/4 means the 4th root of 7, so this could also be written as 4th root of 7. You could evaluate it as the square root of the square root. If you've got a scientific calculator, you've probably got an expression, mine reads y, or x to the y, where I can put in, for instance, 7, hit my x to the y key, and then 0.25 equals, and I get the 3 significant digits as the value of 7 to the 1/4. So it's the same as the 4th root of 7. How about an expression like 8 to the minus 2? What's a negative exponent mean? It means the same thing as the reciprocal of that number raised to the absolute value of that exponent, to the corresponding positive value of that exponent. So this is 1/64th, and that's 0.015625. We call it 0.0156. If we have a combination of them, that's no problem either. Say this original example was 7 to the minus 1/4 instead of to the 1/4. I can evaluate it on my calculator the same way as before. Just hit 7 and then x to the y and then minus, put in a negative 0.25 to get 7 to the minus 1/4. Or I should be able to recognize this is also the same thing as 1 over 7 to the 4th to the 1/4. That is 1 over the 4th root of 7, which I can say 1 divided by 7 x to the y, 0.25 equals, and I get a 0.0357. This was supposed to be the reciprocal of this answer, so I think I'll hit the reciprocal key, make sure it comes out the same. And I get 28 as the reciprocal of that. So 1 divided by 7 invert x to the y, 0.25 equals, and one of my calculator keys isn't working that well. This time I get 0.615. I'll take the reciprocal of that. There's the key that's not working well. And I get 1.63, which is what we had up here. Shows the value of checking if you get a chance to. If you have some way of checking your answer, go ahead and check it. Okay, next, let's look at some units conversions. Units conversions are carried out by multiplying by a well-chosen 1. For instance, suppose I want 55 miles per hour converted to meters per second. I can say that's 55 miles per hour times 1, and 1 is what I want to write. Let's write 1 in such a manner as to get rid of the miles. I look up in the front flap of your text to get the conversion factor between miles and meters. It doesn't give me that, but it gives me, oh, here we go. 1 kilometer. 1 mile is 1.61 kilometers. So kilometers is a kilometer is 1,000 meters, so I'm on my way there. 1 mile then is 1,610 meters. 1.61 kilometers, which means 1.61 times 10 to the third meters, or 1,610 meters. So 1 mile. Okay, I choose my 1. Just the ratio of something to itself is always 1. I choose my 1 in such a manner as to get rid of the units that I'm trying to get rid of. So I'll put, multiply that by 1 in the form of 1,610 meters divided by 1 mile. Since 1,610 meters is 1 mile, this ratio is just 1. I haven't changed the value of the whole thing. But since I get the miles on the bottom, a mile divided by a mile, that's also just 1. I can cancel those, and I've gotten rid of the miles in favor of meters. Now I got to get rid of the hours. I'll put an hour up top here. And there are 3,600 seconds to an hour. You could do that in 2 steps, 60 minutes to an hour times 60 seconds to a minute. But it's 3,600 seconds to an hour. And that's a 1. 1 hour divided by 3,600 seconds is just 1. 3,600 seconds is just another way of writing hours, an hour. And I've chosen the hour up top so that it would cancel the hour down here. And now all I'm left with is meters per second. So just a matter of getting out the calculator. 55 times 1610 divided by 3,600 equals 24.6 meters per second. We call it 25 meters per second if you want to get it to the same number of significant digits that we started with. Very roughly half. So when you're cruising down the highway at 55 miles an hour, you're going 25 meters per second. Since we have a lot of speed limits of 55 miles per hour, that's the speed that you're familiar with. And you should recognize when you're doing that, you're also going about 25 meters per second. Okay, next on our list is shapes. Some characteristics of some shapes. Some formulas concerning circles, for instance. A circle characterized by a radius, r, a diameter, I'll call that d, and of course that's just 2 times the radius. D is equal to 2r. Can be characterized by a circumference. Okay, how far is it all the way around the circle, where the circumference is given as 2 pi r, result from geometry that you should memorize or have memorized, and the area. We'll characterize the area A of a circle. A is pi r squared. Some characteristics of a circle. Okay, next we got the cylinder. It's got a circular face up top, characterized by a radius, r for instance. Same kind of circle on the bottom. And a height or a length. We can talk about the surface area of a cylinder. It'll be the area of this top plate, so the total outer surface area, the area of this bottom circle, and then the area of the cylindrical portion itself. So we could say, we got the area of this, plus the area of the bottom plate. This one's 2 pi r. This will be 2 pi r squared. Pi r squared. And then we've got this part. Imagine it a tin can. You cut off the top and the bottom, and the outer area, the area of the outer surface of this tin can would be the area of the end caps. Plus, let's snip this thing, the remaining portion of the tin can. Once you take the top and the bottom out, snip it down that way and roll it out so that you get a shape about like this, where this part all the way around here is the circumference of the circle, and this side will be the height, h. So the area of this portion is just the width times the height, 2 pi times r times h. So the total area, pi r squared plus pi r squared, that's 2 of them, plus 2 pi r times h. That'll be the area of the cylinder. The volume of anything, volume of some object, is, well, as long as it's got a constant cross-sectional area, and the area of any of these circles, or any circle that you would get by slicing through this right circular cylinder, is the same. So we've got the constant area, constant cross-sectional area. We just take that area times the height, and that gives us the volume. So the volume in our case, the area of one cross-section, just the pi r squared, times the height, h. Let's look at a box now. You have a height h, width w, length L, and the volume, well, the area will be the area of each one of these faces. We got 4 of them, well, 2 of them that are this size, this one, and then one on the other side, which has an area of L times h. And we got the top and the bottom. We got to add, so we got 2LH plus the top, W times L, so 2WL plus 2 W times H, the area of the front and the back. The volume, as you know, just the product of the 3 lengths. You'll probably remember that one. You can think back to that right circular cylinder. In this case, this is the cross-sectional area right here, or I could think of it as a cross-sectional area. The area is H times W, and the length of the thing L. So again, the volume is just the cross-sectional area times the length, or one could do it, think of it as the cross-sectional area times the height. If we stand this thing up on end, the orientation doesn't affect the volume of the object. Okay, next, percent change. This mostly just a wording situation. In dealing with quantitative questions of change, be careful with your wording. So for instance, I go to the racetrack with 20 bucks and I come back with 12. What's the change in my funding? You would say change in funding is minus $8. How did you get that? The change is the final value minus the initial value. So the change in any physical quantity, I call it x, use the symbol delta x. And I've chosen a simple enough example that you can just work it out in your head. All your change in funding, obviously you started with 20, wound up with 12, your change in funding is minus $8. You lost $8. But in cases where you can't work it out in your head, you might want to use the formula, some expression. You should recognize the change in the quantity. In this case, the change in funds available is the final value minus the initial value. It works that way every time. If I say, what was my percent change in funding? That's the change let this symbol X represent my funding in the particular example I have. It's the change divided by the initial value. Times 100%. It's important to recognize that it's the change with respect to what you started with respect to the initial value. So in my case, I go to the racetrack with 20 bucks, come back with 12 bucks. My change in funds is the 12 bucks minus the 20 bucks minus $8. And then the percent change in my funding is the minus $8 dollars, I'll write it that way, divided by $20. My percent change looks like 40%. My percent change in funding, 40%, minus 40%. If you asked what percentage did you lose, in all these cases the answer depends critically on just exactly what the question is. If someone asks you what percentage was lost, you can say there was 40% loss. How much was lost before? $8. So we get rid of the minus sign when the question is not what the change is, but how much got lost. If someone says, what percentage of the original funding do you wind up with at the end? I'd say I wound up with $12, and the question is what percentage of that is what percentage is $12 of the original amount of funds? $20 is 12/20ths times 100%, 60%. I can't say, a common error is you want to know what the percent loss was, and you're able to calculate, or the percent change, for instance. What's the percent decrease in the gravitational force when you double the distance between two objects? That would be a typical question. And you'll learn that the new force, when you increase the distance between the two objects, the new force becomes 1/4 of the original force. So you might write, if someone just asked, how does it change, you would say F nu is equal to 1/4 of F old. If they asked, what's the percentage change, what's the percentage decrease, you would not say it's 25%. It didn't decrease by 25%. If the force went from F old to F nu, if it decreased by 25%, then that would mean F nu would be 3/4 of F old. it decreased by 75%. It went down to 1/4 of its original value. Typically, you're just asked what happened, and you should write it went down to, or the new force is 1/4 of the original force, or it decreased to a value which is 1/4 of its original value. Be careful of your wording in the answer. In so many cases, people say the force decreased by 1/4. It didn't decrease by 1/4. That would mean it's three-quarters of what it originally was. It decreased to 1/4 of its original value. Okay. So with the percent change, it's usually just a question of the wording. Let's look at some trigonometry. Branch of mathematics dealing with right triangles. A right triangle is a triangle such that one of the three interior angles associated with a triangle is 90 degrees. And we symbolize that with that little box shape. I'll call this angle, this opening between these two lines, theta. This side, I'll say it has a length A, this side has a length B, and this side has a length C. With respect to that angle theta, this is called the opposite. And deciding which side is the opposite and which side is the adjacent, you always have to see what angle they're talking about. It depends on what angle they're talking about. If you're talking about this angle, for instance, up here, this would be the opposite and that the adjacent. But with respect to this angle, this side of length A is the opposite, and this side of length B is the adjacent. The side that's opposite the 90-degree angle is always the hypotenuse. And some of the relationships of importance. Pythagorean theorem tells us that the square of the hypotenuse is equal to the sum of the squares of the two sides. C squared is equal to A squared plus B squared, or C is the square root of A squared plus B squared, arrived at from this equation just by taking the square root of both sides. Then you've got your angles, your trigonometric functions of angles. That is a characteristic of this angle and a relationship between two sides. You have the sine, cosine, and tangent, and the relationships between the sine of the angle and ratios of sides, typically memorized by a device where one says SAC CAH TOA. Maybe you have a story, some Indian chief that goes along with it, but SAC CAH TOA. This one tells us the sine of the angle theta is equal to the opposite over the hypotenuse. Which in our case would be little a over little b. That is the value associated with the length of that side divided by the value associated with the length of the hypotenuse. And I think I said little a over little b. I meant little a over little c here. A over c would be the opposite over the hypotenuse with respect to this angle. The CAH, you're expected to memorize these relationships, and this is the memory device that you can use, SAC CAH TOA, to remember it. The CAH means cosine of theta is equal to the adjacent divided by the hypotenuse. So in our case, it would be the length of side B, or adjacent, divided by the length of side C, the hypotenuse. And finally, the tangent of theta is the opposite over the adjacent. In our case, it's saying the tangent of theta is A over B. As an example of a problem where you might use that, suppose you're given B and theta. So consider these quantities given, and you're asked to calculate A. Well, consider your givens. You got an angle, so it's going to be one of these trig functions of that angle. a side and you want to know the other side. The two that you're dealing with are the opposite and the adjacent. Look for the equation that relates opposite and adjacent. It'll be the tangent of this angle is equal to the opposite over the adjacent. We can write that directly as the tangent of theta is equal to A over B. And I circled the quantities that were given, and we're asked to find A. So we have to solve this equation for A. A is equal to B times the tangent of theta. And that would be our answer. They just said they were given. They didn't actually tell us what the given value was. But some fixed value of B, some fixed value of theta. We find A by multiplying the tangent of theta times B. Suppose, for instance, B was given as 3 meters and theta was given as 35 degrees. I could then write A is equal to 3 meters times the tangent of 35 degrees. To evaluate that expression, I hit 35, the tangent key. That gives me the tangent of 35. And then times 3, 2.10. I note that A is smaller than B. With a small angle here, we've got to expect that on a little check. I want to do one more. I'll do it in a different order. 3 times 35, hit the tangent to give me tangent of 35. Check and make sure my calculator is in degrees. It is. The other option is radians. I got a DEG. You have a DEG or a D in your window telling you that the calculator is in degrees mode. And I get 2.1 again. Okay, how about just a little bit of geometry? Some sums of angles. The interior angles of any triangle, theta 1, theta 2, theta 3 for the interior angles, when added, yield 180 degrees every time. There's a pretty simple proof of that. If I start off with a line right here, I rotate it through the first angle, theta 3, and rotate it through the second angle, theta 2, then rotate it through the third angle, theta 1. I'm right back along the same line, but in the opposite direction. Clearly, I've spun that line around by 180 degrees. The interior angles of a quadrilateral. Theta 4 there. Add up to 360 degrees. But I've just got a line cut by another line. I know one angle, this other angle, when added with that one angle, they have to add up to 180 degrees. The opening, an angle is always the opening between two lines. If we just got one line and say, what's the opening between this segment and that segment? It's 180 degrees, 180 degrees. If you've got a right angle, so a 90-degree angle, split into two angles, by inspection, theta 1 plus theta 2 is equal to 90 degrees. For a right triangle, for instance, that comes in handy for a right triangle. You can say, if that's 90, all three of them have to add up to 180, then these two angles to 90 degrees. So that when I add it to the third angle of 90 degrees, I get 180. Two parallel lines cut by another line. So you got a couple of parallel lines. Whoa, let's make them a little bit more parallel looking than that. The parallel lines, they never meet. Cut by some third line, you can say this angle and this angle are equal. Let's give it a different name, alpha. I'll label them both the same way. Or maybe I'll call this an alpha prime. Alpha is equal to alpha prime, property of geometry. These two angles are equal to each other. These small angles, angles less than 90 degrees, referred to as acute angles. The larger ones, obtuse angles, bigger than 90 degrees. These obtuse angles also equal to each other. And further, these are equal to each other. On top of that, this is the same as that. These are referred to as opposing angles. For that, we just need two lines. Opposing angles are equal says this angle is equal to that angle. Also, this one's opposing this one. So this angle, this opening here is equal to that opening. Some characteristics of geometry. Suppose, let's consider a little problem. Two lines meet at 50 degrees. Another line cuts through both of them, and you're asked, what's this angle? And you could say, a straight line going through here, this angle plus this angle have to add up to 180 degrees, so this angle has to be 95 degrees. And furthermore, the interior angles of a triangle, we've got a triangle form, have to add up to 180 degrees. We've got 95 plus 50 being 145. Another 35 will give us 180 degrees, so theta has to be equal to 35 degrees. Okay, let's try some factoring and expanding. Suppose we've got an expression like ax plus ab plus cx squared. I want ax squared equals 8. When I have a situation where every single term has the same factor in it, like in this expression that I just made up, every term on the left-hand side has an a in it, and I can write that as a times x plus b plus x squared is equal to 8. That process is referred to as factoring out the a, and comes in handy, especially in situations where you're asked to solve for a. There would be a step in your solution for a, referred to as factoring out. It's using the distributive property of multiplication, that is a times the sum of terms is equal to the sum of the product of each individual term with a. So the sum of AX and AB and AX squared, and we're doing it in reverse. Instead of distributing, we're factoring it out. Expanding. Should be able to multiply out, expand some expression like that. Take the first term times the first term in that, plus the first term times the second term, and then move on to the second term here. Plus, we have 5x times a, plus that times the second term, just bookkeeping, 3a plus 3 times x, and that, one can probably simplify it, gather all the x squares together if you're asked to solve for x and the x cubes. We'll go ahead and do that to practice the factoring. On the x squareds, we get a 5 and an a multiplying x squareds. We can factor out the x squared from those two terms. Write it like that. With the x's, we've got a 5a and a 3 multiplying the x's. And then constant terms, the only one that involves no x's, the 3a. This would be the answer if you just asked to expand that out. This is also a correct answer. It's been, for some purposes, simplified a little bit further. It doesn't look all that much simpler. Count the terms here. 1, we get, if I go ahead and multiply that out, 2, 3, we get 2 terms from that one. So 1, 2, 3, 4, 5, 6. And I started out 1, 2, 3, 4, 5, 6. So at least I've got the correct number of terms. And then we'd have to check the algebra just to make sure that I didn't make any mistakes. If you get time, always look over your work. Okay, next, rearranging equations. Algebra, that's what most of it's all about, most of the math. Will just be rearranging terms. So we got some expression like GMM over R squared is equal to B squared over R, and you're asked to solve that for R. First thing we can do, multiply both sides by R, get rid of the fraction over there. That makes that just R to the 1. So I've multiplied both sides by R here. And R over R is 1. R over R squared is just 1 over R. Now I can multiply both sides by R again to get rid of the fraction. R, divide both sides by B squared. And then, to finish it up, get R by itself on the left side. I just switch sides. Let's look at a different example. Say, given given R1, given R, find R2. Well, we want to get R2 all by itself. We can say 1 over R2 is equal to 1 over R minus 1 over R1. Take the reciprocal. And might as well leave it like that. It doesn't really get much simpler than that. We're careful not to say that the reciprocal of a sum of terms, each involving reciprocals, is not just the sum of the terms. I've got to, if I want to evaluate that, if they tell me that's 5 ohms, that's 2 ohms, I stick in the value, take the reciprocal, subtract the reciprocal of this value, see what it's equal to, and take the reciprocal of that difference. Let's try another example. Suppose we're given that b is equal to 1 over a plus x. Asked to solve for x. We can take the reciprocal of both sides. Being very careful to keep in mind, this is not 1 over a plus 1 over x. That reciprocal, again, is not distributive. But I can take the reciprocal of the whole thing on both sides, subtract an a from both sides. And then write the answer. Should also be able to deal with situations where you've got to take inverse signs. Say the cosine of theta plus 4 is equal to a over b. A over b are given, and you're asked to find the cosine of theta. Asked to find theta. Find theta. To find theta, first get cosine of theta all by itself. And then take the arc cosine of both sides. It's important to recognize the cosine function is not distributive. That is, the cosine of theta plus 30 degrees is not the cosine of theta plus the cosine of 30 degrees. You have to add the angles first and then take the cosine. Let's say this is equal to a, and I ask you to find theta. You would take the arc cosine of both sides to get this entire argument by itself. And then I can subtract the 30 degrees from both sides. This is the arc cosine of A, and then once you take that arc cosine, that gives you an angle. You subtract 30 degrees to find out what theta is. We mentioned the reciprocal function is not distributive. None of the trigonometric functions are distributive. The square root is not distributive, for instance, over terms in a sum. And even if the terms are separated by minus signs, they're still terms in a sum. Consider a minus b is the same as a plus a negative b. It's a sum of two quantities, even though it's also defined as the difference between a and b. It's the sum of a and minus b. Point here, square root. This is not a plus r. That doesn't work. If you're working with a situation like that, you want to find r. First, get rid of the square root. You want to get r all by itself, get rid of the square root. The inverse function for the square root function is the square. Square both sides. That gets rid of the square root. Then we can subtract a squared from both sides. Take the square root of both sides. Being careful to extend that square root over the whole thing and recognize it's not the square root of the individual terms there, but just the square root of the whole thing. You have to subtract a squared from b squared first, and then take the square root. Powers, same thing. A plus x all cubed is not a cubed plus x. Cubed, it's a plus x it is equal to this. I'm going to keep this the same. Go ahead and expand these two. I got a times a, that's the a squared. I've got an a times x, and then an x times a. So I got two of those ax terms, and then plus an x squared. And the way it reads, these parentheses are very important. Make sure you include them as necessary. The way it reads, this is a plus x times a squared, and then plus 2ax and plus x squared. That's not what I meant. I got to put parentheses around there to complete the job. I want a plus x times everything in there, not just the a plus x times the a squared, and then the other stuff tacked on. So to complete this, we get an a cubed. I got a 2a squared x. I get another a squared x from the next term here, so that'll be a 3a squared x, a 2ax squared. And I never did take that last term here. There's an ax squared there, so I get plus 3ax squared. And then the last term plus x cubed. It would be better not to, I left out the middleman. It would be better to just do this systematically. Let's do it that way. A cubed plus 2a squared x. Take the first one times the third one now, plus ax squared. Okay, now move on to that second term, plus a squared x, plus 2ax squared, plus x cubed. And then in the next line, combine the terms. I got the a cubed here. 2a squared x plus a squared x gives me 3a squared x. A squared x plus 2a, oops, this is a squared x. Oh, here we go. A cubed here, 2a squared x, and the a squared x gives me a 3a squared x. Ax squared and the 2ax squared gives me a 3ax squared, and here's the x cubed. So clearly, this has these two additional terms. The a squared x, and 3a squared x, and 3ax squared that we omitted had we just assumed that we could distribute this cube throughout. The square root and powers are distributive over prodicands instead of sums. If we've got ax, a times x instead of a plus x, ax all cubed, this is ax times ax, which I can rearrange as a times a, which is a cubed times x times x times x. X cubed works out that way every time. Among prodicands, I can just distribute the power. Same thing with the square root. That's distributive. You can't even do that with the sine. You can't do that. The trig functions, the sine of AB is not the sine of A times the sine of B. You have to, even among prodicands, the trig functions are not distributive. You have to multiply the angles out first and then take the trig function, the sine in our case. Okay, let's look at an example of a problem that calls for use of the quadratic formula. Suppose we've got an equation that reads x squared plus 7 is equal to 9x minus 6, and we're asked to solve for x. We want to get this in the form, the standard form of a quadratic equation, which is ax squared, quadratic equation, one involving an entity, a variable raised to the second power. So ax squared plus bx plus c is equal to 0 is the standard form for the quadratic equation. Ours doesn't have that form. It does involve an x squared, which kind of signals us that we might have to use the quadratic formula, but it's certainly not in this form. So let's subtract 9x from both sides and add 6 to both sides. We get x squared minus 9x plus 13 is equal to 0. And now it's got the form of the quadratic, the standard quadratic equation. The solution to the quadratic equation, typically written x is equal to, and then all the rest of this stuff just involves the coefficients of the x terms, doesn't involve any x's. It reads minus b, the thing multiplying the x term, plus or minus the square root of b squared minus 4ac, where a is the thing that's multiplying the x squared, and c is the constant term, all divided by 2a. Okay, in our case, a is equal to 1, the thing multiplying x squared. There's nothing there, it's just a 1. Thing multiplying the x is our b, and that's a minus 9 in our case, and the constant term is just 13. So we go ahead and use that expression. X in our case then, and it does turn out to be x, could very well be t or some other symbol, works just as well in a quadratic formula as x. X is equal to minus b, it will give us a plus 9, then plus or minus square root b squared is 81, minus 4, a in our case is 1, times c, which is 13, all divided by 2 times a, 2 times 1. Continuing over here, I got 9 plus or minus the square root of 81 minus 52, which is 29, all divided by 2. And of course this corresponds to two values. X is equal to, convenient way to evaluate this expression, take the square root of 29, and store it. And take 9, first I'll do the plus solution, plus, memory recall, that value that I just stored, the square root of 29, equals, divided by 2, equals 7.19. And then I still got that value in there, so I go 9 minus, memory recall, that same value, the square root of 29, equals, divided by 2, equals 1.81. For my two values of x. As an example of a pair of simultaneous equations, let's try ax plus by equals c, and y minus 3x is equal to d, where the unknowns, or the variables, are x and y, and our goal is to find x and y. In terms of known stuff, This, if I just add 3x to both sides, I can say y is equal to 3x plus d, but that just gives me an expression for y in terms of something else that's unknown, the x. There's an x that appears in there. The way to do it, typically, no matter how many of them you get, you take one equation and use it to express one unknown in terms of all the others. Here we've only got two unknowns, so we take one equation and use that one equation to express one of the unknowns in terms of the other. And in fact, that's a nice starting place. Y is equal to 3x plus d, a useful step, but definitely not the solution to the problem. The y, our expression for y, has an unknown x in it. I'll call that equation number 1, 2, I'm going to call this one 2 prime. If I substitute my expression for y into equation 1, then I'll get an equation. If I replace this y everywhere I see it with 3x plus d, as I said, it's equal to y. 3x plus d is equal to y. Then I've got an equation up here that just has the x in it, and I can solve it for x, and I've done half the problem. So making that substitution, I get ax plus b times 3x plus d is equal to c. ax plus 3bx plus bd is equal to c. Solve that equation for x. I want to get all the stuff that has an x in it on this side, all the stuff that doesn't on that side. So I get ax plus 3bx is equal to c minus bd by subtracting bd from both sides. Now let's factor out the x. Every term here has an x in it, so I can factor it out. This equation then reads a plus 3b all times x is equal to c minus bd. Divide both sides of this equation by this expression in parentheses, and I get x is equal to c minus bd, all divided by a plus 3b. Okay, that's half the problem. I got the x, got an expression for x in terms of known stuff. The unknowns are x and y. I don't have any x's or y's here. So the y, I can go back to this equation, 2 prime, and substitute my now known quantity x, my expression for x, into this equation. I get y is equal to 3 times the c minus bd all over a plus 3b plus d. And I'll leave it at that. I could put these over a common denominator and combine some terms in the numerator, but this is a solution. Y is equal to 3 times this fraction plus d. Okay, now let's move on to number 11, graphing. Topic 11. Suppose somebody asked you to make a graph of velocity versus time. The first quantity goes along the vertical axis, the y-like axis. Typically you indicate the meters. And the second quantity, the thing that comes after the versus, goes along the x-axis. Indicate the units, so we'll plot that in seconds. Suppose they say one particular point on the graph corresponds to a car. This might be the velocity of a car as a function of time. At the 7-second mark, the car was moving at 45 meters per second. Okay, our time axis we'd have to mark off in seconds. say 2, 4, 6, 8, 10, our velocity. Let's try 10, 20, 30, 40, and I believe I said they were moving at 45 meters per second at the 7-second mark, whatever the example given. Let's assume we find the car was moving at 45 meters per second at time 7 seconds. Times 7 seconds, that means we go over to the 7-second mark on the time axis and up 40 and halfway to the 50 mark along the velocity axis, and that would be the point corresponding to 45 seconds, comma, 7 seconds. And that's all you need to know for the math preparation. We'll be doing some more graphing as part of the physics course. Graphing trig functions. You should be able to graph the cosine of theta as a function of theta over any range of angles, typically 0 to 180 or 0 to 360, 0 to 720, something like that. Same thing for the sine of theta. So sine of theta or cosine of theta. Suppose I asked you to graph the sine of theta for theta from 0 to 720 degrees. So you'd say, make a graph. Sine of theta starts out at 0. Whoa, I ran out of space there. Better try it again. Bounces back and forth between -1 and 1. That's just a fiducial line, not part of the graph itself. Here's the curve. This is the theta axis in degrees, and this is some important degree marks: 90 degrees, 180 degrees, 270 degrees, 360 degrees, plus 90, it's like 450, 540, plus 90, 630, there's 720. That's how far out they wanted us to go. It completes one oscillation in 360 degrees, and then the pattern repeats. And we just keep on going up to whatever angle they say. That's enough for graphing the sine function. Suppose I asked you to graph the cosine function from 0 degrees out to 360 degrees. The cosine of theta, for any angle theta, never gets bigger than 1 or smaller than -1, so we got those same kinds of limits there. It starts out big. It starts out at 1. And in 360 degrees, it just completes the pattern. Going up, back up to 1, cosine of 360 is 1. Important marks here, that would be 90 degrees, 180 degrees, 270, and 360 degrees. And again, never gets any bigger than 1. It's always less than or equal to 1, greater than or equal to -1. In applying this knowledge about trig function graphs, you use either draw the graphs that we just drew or have them in your mind. When somebody says, for instance, what's the maximum value of 5.2 times the cosine of theta all squared? Well, the bigger cosine of theta is, the bigger this expression is, and the biggest the cosine of theta can ever be is 1. So I pop in the biggest value. I don't bother to put in 0 degrees or 360, whatever. Or when cosine of theta is -1, it'll work too. Is you square the -1 and you just get 1. I don't care, you know, at what angle it takes on that biggest value. I just know the biggest value the cosine of theta can ever take on is 1, and hence I just replace that with 1 if I'm asked to find the maximum of this expression. So let's say y is equal to that, and you're asked for find y max. You're asked to find y max by inspection occurs when the cosine of theta is 1, as we argued. And that is 5.2 squared. 27.04, 27.0 is the maximum value that this expression can take on. Had I asked if I stuck a sign in there, you would say, well, the biggest it can ever get is 1. I'd get the same exact result if that was the sine of theta. If I asked you what's the minimum value that y can take on, you might be tempted to say, well, the smallest value you can take on, that occurs when cosine of theta is its minimum value, which is -1. But again, because this gets squared, any negative value gets squared, and our y, by definition, that y is equal to 5.2 times cosine of theta all squared, is always positive. So the smallest it can ever get is when cosine of theta takes on its smallest absolute value, and the smallest absolute value that it can take on is 0. It crosses through the 0 line. Picture that graph again of cosine of theta versus theta. It crosses through the 0 line at 90 degrees, again at 270. We don't care where it crosses through. We just recognize that the minimum value for y occurs when this part is 0, so y min is just 0. This is 0 times that is 0 squared is 0. That concludes our review for the math test. Review of your math skills. Good luck on that math test.